Okay. All right. Lecture 5. Did you all have fun with the homework? You're like, man, Dr. Mike, your definition of fun is kind of interesting. It's questionable, yeah. Okay, so let me talk a little bit about some topics moving forward so that hopefully it allays your concerns. So yeah, I imagine that of the recent homework assignments that we've had, that the one that you just submitted was probably the most challenging so far. And that's a little bit by design. We're going to sort of revisit the topic today from another angle, as it were. We're going to look at two forces and look at the resultants, but we're gonna look at it from a different perspective. What I will tell you is that the homework, this homework that you just submitted, I know was probably a tad challenging. And I'll go ahead and tell you, I think the homework that I'm submitting or that I'm assigning today, I don't think it's as challenging, but I think it's kind of a similar ilk. But after this, it gets better because what we're going to do today is we're still going to look at scenarios with two vectors and trying to assess the resultant of those two vectors. But afterwards, I mean, we're going to start to ask the question, okay, I know how to add two vectors. What about adding three vectors or six vectors or whatever? And that would be pretty cumbersome to do from a trigonometric perspective, because what you'd have to do is if you had a point that had six vectors on it, then you'd have to add two of them and then get that resultant and stick the third one on there and do the resultant for that and then do the resultant for that. And then you'd have to keep doing it over and over again. And that would get pretty cumbersome. And so we're going to introduce a notation. If you've had Calc 2 or Calc 3, if you remember we mentioned this before, it's a standard way of expressing vectors through the use of unit vectors. We have these unit vectors I, J, and K that we utilize to express vectors in a standard fashion. And converting vectors into an IJK format allows you to add those vectors very, very easily. The other thing about IJK format, and this won't be an issue until exam 2 land, but in addition to, on top of needing to add vectors, we're also going to need to learn how to multiply vectors. And there are actually two ways of doing it, and it would be pretty difficult to do, three-dimensional vector multiplication without that notation. It'd be pretty tough. But with the IJK notation, it makes it a lot simpler. In terms of some other announcements, so I will actually be out of the office tomorrow. I have to go out of town for a meeting with my research agency, but I'll have access to Teams and whatnot. I mean, I'll definitely be within, Wi-Fi access and all that. So if you have any email questions, you can email me. You can message me on Teams, and I'll get back to you. Again, I think this homework will probably be a little bit easier than the one you just submitted. I do want to mention also an employer highlight series, employer spotlight series that we're starting this semester. I imagine that many of you, on top of just wanting to be engineers, are getting college degrees because you like jobs, right? Jobs carry with them money, and I don't know about you, but I like money. We're having a series of employers come throughout the semester. They're going to be in Shockey at 1 p.m. for all of these sessions, except for the October 6th session is going to be in Don Morse room. So they're all in the Student Center. The first one is on September 8th. It's with the DOH. So for you civil engineers in the room, that might be something you want to think about attending. And even if you're not a civil engineer, they do a pretty robust summer co-op internship experience. And there have been mechanicals and whatnot that have done that over the summer as well. The contact information for registering for that event is on this slide, and this slide is uploaded on Blackboard. You can just contact Tanner Drown, our co-op coordinator. His email address is drown12@Marshall. It's a sort of a first-come, first-served basis, but they've said that students, engineering students in CECS and whatnot will get priority. And there'll be lunch, so yay for food. The only thing is, this is, so when it's Wednesday, September 8th, and it's at 1 p.m. I just realized that's when we have class. I'll say this. If you want to go for one of these sessions, I mean, you can go, let me know, and I'll excuse your absence, but let me know. If I don't know, I'm just going to think you're absent, okay? I'm going to, now keep in mind, I'm going to record the lecture, and you're still going to be responsible for the homeworks and whatnot, but I won't count you down as absent. I won't lower your absence grade. Sound like a plan? Okay, so let's get into vector land. Is this not working? Maybe the battery's low. Oh well. Okay, let's go back. Let's just get back into the frame of mind of what we were talking about on Monday. So we introduced two mathematical objects, scalars and vectors. Remember, scalars are basically just numbers because all they carry with them is a magnitude, and vectors carry with them magnitude and direction. That's what makes a vector special. Vectors can be multiplied by a scalar to change their magnitude, and if you multiply by a negative number, that just changes its direction. It flips it about its line of action. One of the things we will start to use soon are unit vectors. So a unit vector is a vector that has a length of 1. Its magnitude is 1. It's a way of separating the magnitude and the direction mathematically, and there's a lot of benefits to that. IJK notation does that because IJK, those are unit vectors. Those are vectors with a length of 1. So that'll be something we talk about not too long from now. When we add vectors, we add them following this tip-to-tail fashion. So if we have, let's say, these vectors P, Q, and S, if I wanted to determine vector P plus Q, I stick one vector at the end of another, and then the resultant is just connecting end to end. Remember, the order of operations does not matter. You can do P plus Q, and it is the same thing as Q plus P. So vector addition, the order doesn't matter. Vector multiplication, depending upon the type of multiplication, the order does matter. But that's down the line. We'll talk about that later. So everybody okay with the concept so far? I know probably that homework was challenging from a trig perspective, but by and large, I hope that the ideas are pretty straightforward. So far, so good? So what I want to do is I want to use this knowledge, and today might be a pretty short lecture because I just want to do another example and give you a homework with an additional example using this tip-to-tail methodology. But we got a little bit of a different problem today. What we did last time is we said, here's vector A, here's vector B, add them. That's simple. That was it. Today, we've got a little bit of a different challenge. So let's take a look at the problem. We have a vehicle, and we're trying to pull this vehicle, maybe it broke down or whatnot. Maybe it got stuck on Fifth Avenue. Man, did anybody get stuck on Fifth Avenue the other day? I got stuck. It was pretty rough. It took me about an hour and a half to get home, whatnot. That was not a fun ride home. But we have a vehicle stuck, and it's being yanked on by two ropes, okay? So there's a rope, we'll call this rope AB and rope AC. So they're both connected to the car at point A, okay? And we know how much tension is in the first rope. So we know everything about vector AB, okay? So vector AB, we know that the magnitude of that vector is 3 kilonewtons, and we know the direction because measured from the horizontal, it's 30 degrees, okay? Now, what we don't know is what's going on with this vector. So we know the car is being yanked on with two ropes. We know what's going on with the first rope, but not with the second, okay? And I want to determine what's going on with this second. Well, how do I do that? Well, I look at the goal. For this problem, I want the goal to be that the resultant be horizontal, okay? And I think that makes sense from a common sense standpoint. If I'm yanking a car, I'd want to yank it that way, right? So I know I want the resultant to be going that way, and I want the total resultant force to be 4.8 kilonewtons. Maybe you did the math and you figured out it would take 4.8 kilonewtons of force to start moving this car So you know one rope is yanking this way. How much does this rope need to yank, and at what orientation, so that the resultant is horizontal? Does that make sense? Okay. So what we're going to do ultimately is try and figure this out. The magnitude and direction of this vector here. We'll call it T sub AC. So T because I'm talking about the tension in the rope, and AC because that's the indicator. And remember, anytime that I type out a vector, I'm going to use that bold letter because bold letters reference vectors. And when we write it by hand, we'll just put like a little arrow atop T and whatnot. Okay. Let me pull up the notebook. So there's nothing here that isn't already on the screen and whatnot. So this should be pretty straightforward. Okay. So let's write down some facts that we know. Okay, before we start getting into this. Let me get my mouse pointer, get this out of the way. Okay. So here's our situation. I think that we should be able to write the following. Let's talk about TAB. Okay? Actually, let me write it a little bit lower because I don't want to squunch this. Let's write this right here. Let's look at the tension in AB. Okay? Notice it's a vector because I'm writing that little arrow on top of it. And what I'm going to do is write it like this. I'm going to write that it is 3 kilonewtons at an angle of 30 degrees. All right? I think that would be a fair way of doing that. Now, if that's the case, I want somebody to tell me what the resultant would be written as. If that's how I would write the tension in that first rope, how would I write the resultant? What's the magnitude going to be? 4.8 kilonewtons. And measured from the horizontal, what's the angle? 0, because the whole point is that it's supposed to be horizontal. So I'm just making sure that we're on the same page here. So 4.8 kilonewtons, and then 0 degrees. And then what I might do for this one, sorry, hold on. For what I might do for this one is I might say, some force, and probably what I would do is reference that angle like that, right? Because it's going to, obviously, I'm yanking TAC down something like this. So ultimately, that's what I want. Magnitude, direction. So let's see if we can figure this out. All right, let me scroll down a little bit. Okay. So the first thing that we need to do is we need a graphical representation, which I think you're going to find is pretty straightforward. But let's see what we can come up with. So what I'm going to do is I'm going to use this tip to tail fashion like we've done before. And so I've got vector AB and I've got vector AC. So I'm going to move that vector AC up like that. So it's going to be AB and then AC. And so from A to C, from A to that end is going to be the resultant. And remember, the resultant is going to be horizontal, right? So let's see what that looks like. Maybe it looks something like this. So let's draw point A down here. So that's point A. And let's draw vector AB. So this is the tension in AB. Okay, so let's see what we know here. So I've got this vector. What does this mean again? The magnitude of AB. That is 3 kilonewtons, right? And then what I'm going to have is a second vector going like this. So TAC. Now I don't know that magnitude, right? I don't know that. But I do know that this is going to be my resultant. That's my resultant. Bless you. And then the magnitude of that resultant I know is 4.8 kilonewtons. Now, let's see if we can identify some stuff to solve this out. Like I said, today's probably going to be kind of a short lecture. Are there any angles in this triangle that we know? Yes.
Angle A,
This angle. And what is that?
30 degrees.
30 degrees. Exactly right. That angle is 30 degrees. Now, let's see if we're paying attention. Is there any other angle that we can identify? And let me, to help out, what I'm going to do is I'm going to cheat a little bit. We'll move this up a little bit so I can scroll up. Now, is there any other angle that we can identify? Yes?
Could you maybe say that angle between TAC and the resultant would be, what do you call it, theta?
Yeah, so this symbol here, yeah, alpha. That's exactly right. Now, how did you do that? Well, let's look at this diagram here. Okay, let's do a little thought bubble over here off to the side. Okay, so here's this, and here's AC, tension AC, and this angle here is the Greek letter alpha, right? Looks like a little fish, like if an A and a fish cross paths. Remember geometry? Remember parallel lines cut by a transversal, right? If I have two lines cut by a transversal, then this angle and this angle are equal. I know that's a very, very small diagram. But the idea is that here's that resultant, and so that's going to be alpha as well. That's exactly right. Does that make sense? So that means that this angle here is alpha. If you understand that, the rest of this is going to be pretty rote. It's going to be pretty simple. Okay. So help me out. You help me out, because the first one when we did this lecture on Monday, I sort of did it myself, but I want you to help me. I want you to engage a little bit. So here we've got a triangle. We know this side, we know this side, we know this angle. And what are we trying to find in the problem? We're trying to find this magnitude, and we're trying to find this angle, right? Because that's what we need to know, the magnitude of the rope and the angle. So help me out. Let's start off with this. What would you do? What would somebody raise their hand? What would you do to solve that? Yes? The law of cosines, exactly right. So let's do that. Let's find the magnitude of TAC using the law of cosines. The magnitude of TAC using the law of cosines. And the reason we're using the law of cosines is because we have a triangle, we know two sides and one angle, and those quantities are all bunched up together, like it's two sides and the angle between them. So the law of cosines is really it works very well to determine that opposing side. Now, what I'm going to do just for shorthand, if you remember, note, if you write, like, if you have some vector f, if you just write f, that's basically saying the magnitude of that vector. So I'm just going to reference this expression in magnitude, so because that's what we're solving. So here's how I'm going to do this. So TAC equals. So remember the law of cosines. I'll put that also in a little thought bubble. The law of cosines states that a squared equals b squared plus c squared minus 2bc cosine of a. So TAC is going to equal, let's see if we can write it out symbolically. So it's going to be TAB squared plus r squared minus 2 TAB r cosine 30 degrees. Is that right? Yeah. Did I forget something?
Square root.
Square root. Because I'm solving for that length, I got to square root that whole thing. I got to square root that whole thing. So, equals TAB 3 kilonewtons squared plus 4.8 kilonewtons squared minus 3 kilonewtons, 4.8 kilonewtons. Square root of all of that. I'm going to give everybody a sec and see if they can figure this out. Which, by the way, I wanted to show y'all something just because I have a software package installed on this machine, which is an emulator for the Casio, which even if you have like a TI or something like that, we're going to have some exercises where we're going to be doing things like solving 2x2 systems, solving 3x3 systems and whatnot. And so I might bring this up here so you can see the calculator, and then there's this pop-up display where it's kind of magnified. So hopefully that helps out with being able to read it if you're sitting there in the back. Okay, let me go back here. Does somebody have an answer for that tensile force? We'll say to 2 decimal places. Yes, sir. 2.66 what? Kilonewtons. 2.66 kilonewtons. Do I have a second on that? There we go. That is correct. And so that's how much we have to yank on that second rope in order to ensure that the resultant is horizontal. But what it doesn't tell us is at what angle. And so in order to determine that angle, we need to determine alpha. So let's go back to the triangle. At this point, we could do it a number of ways. Personally, I think that the law of sines is a little bit easier. The formula is a little smaller. So what we can do is we can say, I don't know, the sine of 30 degrees over this equals the sine of alpha over 3 kilonewtons, right? Remember, it's opposites, right? So maybe I'll do that symbolically so that we can follow it. So let's look at direction of TAC using the law of sines. So, let me see if I can do this right here so we can still see. So what I'm going to do is I'm going to utilize opposites. Remember, my goal is to determine alpha. So I'm going to say that the sine of alpha divided by TAB, right? Because here's my triangle, and the way the law of sines works is you have to use opposites. So this angle and this side, the side opposite that angle. So sine of alpha over TAB equals, and then I need a pair of values that I do know that are opposites. So I know this angle is 30 degrees, and I now know TAC because I just figured it out. So that equals the sine of 30 degrees over TAC. So now what I can do is I can solve for alpha. And so how do I do that? Well, the sine of alpha, what do I do for the sine of alpha? Multiply both sides by TAB, so that the TAB cancels over here on the left. So we have sine 30 degrees TAB TAC. And so alpha is the inverse sine of that. And so what was TAB again? Was that 3? Or the TAB, the magnitude of that first rope? 3. 2.66. Let me scroll a little bit, so because I know that's probably kind of low for some of you. Let's do that. There we go. What are we getting for this? Yes?
34.33 degrees.
34.33 degrees. Okay. Do I have a second on that? I got multiples. There we go. So there you go. What's going on with AC? Well, we got to yank it 2.66 kilonewtons at an orientation 34.3 degrees. Let's stop for a sec and absorb that. Let me ask you this. Was this one as bad? I think that, I kind of think this one's easier than the last one, even though if you describe the problem, it sounds harder. The last problem was just take 2 vectors and add them up. Now I'm going to give you one vector, and now you need to figure out the other vector so that the sum looks like this. It sounds harder, but I don't know. For me, it seems easier. So I don't know about anybody else. Does anybody have any questions? So let me tell you a little bit about your homework. So your homework is going to be very similar to this, but it's oriented a little differently. So the idea is that instead of the resultant being horizontal, the resultant needs to be vertical. So what's going on is there's a box, and it needs to be yanked up, right? So one rope is yanking this way. What's the magnitude and direction of the other rope so that the resultant is vertical? That's basically what we're doing on the homework. Let me see something real quick before we call it, because that's pretty much all I had for lecture. I might just give you a little bit. Oh, I didn't mean to close that. So does everybody still? Do y'all have this or? Okay. I might just give you a taste of what's coming up in the next lecture. It's got a lot of notes to it, but it ends up being pretty simple. See, here's what we're going to do for the next lecture. I'll just give you a little bit because we're going to end here in a second. And I want to explain why this IJK notation is so valuable. So what we're doing here right now, and to be clear, what I'm talking about right now is not on your homework that's due on Friday. But what we're doing is we're basically dealing with vectors 2 at a time. And I said if you wanted to try and add 3 vectors or 4 vectors or 5 vectors, it would be real cumbersome to try and do it in this tip-to-tail trig fashion. Well, what we're going to do is we're going to come up with a new way of doing it, and the new way of doing it is basically going to be splitting vectors up into x and y components. See, any vector, this vector f, I can take that vector and represent it as fx plus fy. Because think about it, right? Here's the vector f, right? So what can I do? I can say, all right, tip to tail. I can go over x, up y. There's the vector, right? Wouldn't matter which way I added, I could do up y and over x. But the idea is that I can split that vector up into x and y components. Why is that valuable? Because I can do that with a number of vectors. I can say, what if a point has 12 vectors on it? I could take each of those vectors, split them up into x and y components, and then add up all the x components, add up all the y components. There's your resultant. Okay? It's a little bit more straightforward. And what we'll do in order to standardize our notation is we're going to introduce this concept of a unit vector. The idea that we have a vector that has some magnitude and direction. We can separate the magnitude and direction out by defining a unit vector that just has a magnitude of 1. And we have a standard set of unit vectors that we use in mathematics, and we call those IJK. So, for instance, the definition of the I vector is a vector that goes along the x-axis and has a magnitude of 1, and the j vector is a vector that goes along the y-axis and has a magnitude of 1. And for 2D problems, we're just going to use I and j. We'll throw in the third dimension a little bit later. And then the idea is that gives us a standard way of referencing all of our vectors. I don't want to get too far into the weeds on the next lecture on Friday, but the idea is that this will give us a much more standard way of handling problems with multiple vectors. The problem that we do on a Friday, we're going to add 3 vectors. And instead of doing this tip-to-tail fashion, we're going to split them up into x and y components, and it's going to be a lot easier than what we've been doing now. What we do with IJK notation later on, we're going to be able to do some really interesting stuff with it. 3D, moments, where we're multiplying vectors. So it's a very integral part of this course. You will see IJK notation later. I think it's Calc 2 or Calc 3. It's probably Calc 3 here at Marshall when you start doing vector calculus. But it's a very common way of expressing things. Bless you. Any questions before we call it? All right. This is the last, I would say, sharply painful trig homework, and then it gets better. That's all I've got, everybody. I will see you all on Friday. Again, if you need me, Teams or email. I won't be here on campus tomorrow.